Whether we are purifying water, alcohol, or the medicines that keep us alive, distillation is a key tool in the chemist's arsenal. In this video, we will look at how distillation can be used in the modern chemical laboratory, and we will cover the key aspects of this technique that you will need to know to get a GCSE in chemistry. Welcome to the third of our separation technique videos. There is a general overview available and that is linked above, but today we're going to focus on the details of this important technique, distillation. Distillation is a technique that allows for the separation of one liquid from either a mixture of liquids or from a solution. I'm going to start off by showing you how distillation is generally done in the lab, and I'll go through the key points of that technique, and then I'll demonstrate a stripped down version of the technique, such as you might be asked to carry out in a GCSE chemistry laboratory. For the purposes of this demonstration, my initial mixture is just some water combined with some food colouring. The food colouring has a much higher boiling point than the water does, and so I should be able to get a very clean separation between these two substances. In a modern chemical laboratory, apparatus such as this is likely to be used. The key piece of equipment here is this, a Liebig condenser, and although it looks complex, it has a very simple job. It is designed to rapidly cool a hot gas and cause the particles to condense back into the liquid state. It is really just two glass tubes, one inside the other. The inner tube carries the hot gases from this vessel here, all the way through and down to this collection point here, while the space between the two tubes is filled with cold water. Before I go any further, I need to connect up my cold water supply to the condenser. I'm going to put the cold water in at this lower end here, so that I can get a gentle trickle of water to flow through, which will gradually fill up the gap between the two tubes, carry up here and down and into my wastewater down there. This is so that I can gently fill the tube until it just overflows with water, as this will allow me to maintain a steady supply of cold water without needing to use vast quantities of water to achieve it. Depending on your exam board, there could even be a mark available in an assessment for correctly labelling the in and out points of that cooling water. But regardless of that, this is still good laboratory practice and well worth knowing. And now I'm going to adjust the temperature on my hot plate here and begin to warm my mixture towards the boiling point of the most volatile component, which in this case is water. Now, quite often we're distilling components other than water, many of which can be flammable, and so it's good practice to use an electrical hot plate heater such as this one here, rather than a Bunsen burner, because that will reduce my risk of fire. This is a small technical point, but it is worth noting that I've positioned the bulb of my thermometer right here, next to the point where the gases are going to draw off down the tube, which is going to allow me to get a very accurate temperature of the vapours that I am condensing. You also might just be able to notice that there are some ceramic chips in the bottom of this flask. They're certainly not getting involved with either of the chemicals, but what they are doing is just giving the gas bubbles that will form a surface to form on. They are called anti-bumping granules because they stop big bubbles bumping my solution up and then down my tube here. And as such, they perform an important function, although they're not involved in any chemical process. As we reach its boiling point, this space here fills with vapour. Our clue that this is happening is the condensation that's appeared and the fact that the temperature on the thermometer has now rapidly risen to the boiling point of that fraction, which in this case is 100 degrees C, and indicates to me that I am collecting water. It's good practice to throw away, to dispose of the first couple of millilitres of a liquid that comes across. And if I was doing this to collect pure samples for use in analytical chemistry, that is certainly the first step I would do. As I continue to provide thermal energy, the temperature now stays constant at the boiling point of my component, but the gas has begun to condense on the walls of the condenser all the way down here, and liquid is now running down and dripping out at a rate of 1 drop every few seconds. I'm going to leave this running for about another 5 minutes to collect sufficient sample, and then I will turn the temperature off. And so here's the water that I collected. In this case, this water will be pretty pure, as almost none of the food colouring should have evaporated and come over with it. This is an important point. Remember that every liquid evaporates to some extent, and the closer we get to the boiling point of the liquid, the more of it will evaporate. Let's look at another example where this is going to be critical. This time I have a mixture of ethanol and water, which my alcohol refractometer here tells me is 20% ethanol. I thought it would be useful to show you how all of this equipment is assembled. First of all, I've got my round bottom flask, which contains my mixture and a few anti-bumping granules so that I get a nice even boil. And then I've got to put this little adapter in place here first, and that just goes in there, followed by this, which is the still head, which is going to connect this equipment to the Liebig condenser. And I'm just going to pop that in there like this. Next, I've got to connect up the Liebig condenser. And actually, this is the point where most problems happen, because if I don't loosen these joints sufficiently to allow this to move and adjust as it goes in, I could put pressure on my glassware and potentially break it. So I'm making sure that I've got loose joints as I attach it, and then I just tighten them off slightly, just gently, just to hold it in place. Then the last part of this really is the thermometer, which again, as I put it in, I just need to make sure, and obviously I've pre-adjusted this so it does work, but I'm checking that the bulb of my thermometer lines up with the connection joint to my condenser. I'm then just going to add a little bit more water to this, just so I get a gentle flow of water through my equipment. And then it's just a case of turning on my heater, which is set this time to get the oil bath to 100 degrees because I'm going to boil my ethanol at about 78 degrees. The last bits of equipment to connect is just this little attachment at the end to help the liquid eventually come down into a beaker, which I'll place here in a moment to catch the ethanol as it condenses inside my Liebig condenser. And I've got 2 little beakers set up here ready to go. One to collect the first few centimetres cubed, which may or may not be pure, and then one to collect the majority of my sample, which I will then test. Okay, so I've now collected probably about 2 or 3 millilitres of distillate here. That may or may not be pure. So what I'm going to do now is just remove this beaker and replace it with a clean one. And then this becomes waste. And then I'm just going to wait until I've collected enough sample that I'd be able to test it. So that's going to take probably about another 5 minutes. Now, I've been distilling for about 5 minutes and I've collected about 10 centimetres cubed of distillate here. I've just turned my heater off, and the reason I've done that is I've got enough to test and I'm not interested in collecting large volumes of ethanol. The reason for that is it's actually illegal to distill ethanol in the UK without either a distiller's licence or to be doing it for the purposes of teaching chemistry. So I've got enough here for teaching chemistry, and I'm going to have to destroy this safely at the end of the experiment, which I'm going to do by just setting it on fire. Before I do that, I'm going to test this sample for purity, and I've got my alcohol refractometer here. If I take a couple of drips of this distillate, place it on my screen, close my little window here, and then look through this, it will tell me the percentage by volume of ethanol in this solution. So I guess the question we've got to ask ourselves now is this pure? Well, my refractometer tells me that it's only 75% ethanol. So what went wrong? Well, nothing really. It's just that 78 degrees Celsius is very close to water's boiling point, and so a fair few molecules of water were in that vapour as well. And that's really just the limit of distillation. The fractions, that's what we call those separate components that we collect, are rarely pure unless their individual boiling points are very far apart. Now, it's worth mentioning that although I'm allowed to distill small quantities of ethanol for the purposes of teaching chemistry, I must destroy the distilled product. And so I'm just going to set it on fire in this little basin here to complete my experiment. And there we go, my ethanol is turning into carbon dioxide and water. So, as you'll see, I've put that equipment away, and what I've got out in front of me instead is a kind of reduced version of it. Most GCSE exam boards have a required practical activity where students carry out a distillation, and it's often combined with the purification of water. Here, I have a sample of very salty water, and my task is to remove the salt from it and collect a sample of clean distilled water. My equipment is much more limited than before, so I'm going to put the water into this boiling tube here. Again, I'm going to add a few anti-bumping granules, and then I'll put this bung in the top, which is already connected to a little glass delivery tube and some rubber tubing. If you were assembling this yourself in the lab, you'd need to be very careful not to break the glass tube, as cuts from broken glass present one of the biggest hazards in this experiment. At the other end of my tube is another section of glass, and that's going to get inserted into the bottom of this boiling tube here. So I'll just assemble that now. So that's going in there like that, and then this piece here, that's going down into here like that. When I turn on my Bunsen burner, I'm going to heat the mixture here. Water vapour is going to form. It's going to pass up along this tube, down here, and then arrive in the bottom of my boiling tube over here. The problem I've got is that at no point on this journey is it going to get cooled down. So to replace my expensive and complicated condensing equipment, all I'm going to do is chill this tube with some iced water. So I'm going to take some iced water, and then I'm just going to carefully lower my boiling tube into the mixture of ice and water, and then I'm just going to again lower this little support for my glass delivery tube. At this point it's time to light my Bunsen burner, so I'm going to pop my safety glasses on. I'm going to check my air hole is closed. I'm going to add a little bit of gas, adjust my flame height slightly and set it to the roaring blue flame. And I just simply have to gently heat the water here. At no point do I want those bubbles to rise up too high, because that could cause bubbles of the mixture to get into my tubing, and that would contaminate my distillate at the other end. And rather like in the evaporation experiment in the previous video, I do have to continuously adjust the position of this flame. Too hot, and my water will boil too violently. Not hot enough, and once again we'll be here all day. By the way, the other big risk here is scalds from the steam, and these can be very nasty. And that's why I've got everything clamped down securely. Don't try to do this by getting your lab partners to hold the glassware stable for you at the bench, as that could really cause a nasty accident. As I stop heating, there's one thing I'm going to need to do quite quickly, which is to lift that delivery tube from out of the distillate that's come through. I'll explain in a moment. First of all, I'm going to pop my Bunsen burner down, and then I'm very quickly going to lift this tube out. Why did I need to do that so quickly? I needed to do that because as I stop heating here, the air pressure will change inside this tube. It will then suck my solution back up here if I don't lift it out of the water, and then all of my good work would have been undone very, very quickly. Secondly, the problem is that this equipment is all still quite hot. So now you can see the importance of this little metal ring here, because it's allowed me to lift that glass tube out of my delivery vessel, this boiling tube here, without having to touch it. And in fact, I'm now not going to touch any of this equipment for about 5 minutes while it all cools down. Well, my equipment has cooled down enough that I can now take off my safety glasses and disassemble my equipment. Just careful that I don't knock the glass on anything on the way out, because it is very fragile. And then I can have a look at what I've got. I've certainly lost material from this end here, and when I have a look at what I've got over here, I can see I have a sample of clear liquid, but the only way I'm going to be sure what I've got is if I check its boiling point. So having checked the boiling point of the water, I've found that it is 100 degrees Celsius, and that is one of the tests that you're required to know at GCSE to confirm that you have pure water. The important point here is that a little still, like we set up here, could be quickly assembled out of basic equipment to provide clean, safe water in the case of an emergency. And you can even buy versions that use the heat of the sun to get clean, drinkable water from seawater if you're lost at sea. So, we've seen what distillation is, we've seen how it's carried out in a research laboratory, and how it can be done in a simpler way at a school lab bench, or to provide fresh water in the case of an emergency. As always, this video is supported by a worksheet on my Patreon page, and all I ask is that you add a like to this video and subscribe to the channel so that I can continue to help more chemists around the world. Thank you for watching, and I'll see you next time.